Dear students, good morning. In the previous classes, we have discussed about various algorithm design techniques such as divide and conquer technique, greedy method, dynamic programming. In today's class, we will discuss about one more algorithm design technique which is named as a backtracking. Before going to learn about the backtracking, let us discuss about previous techniques once. The first technique, divide and conquer. So what is the general method for divide and conquer? Here in this method, if the problem is very large, we will divide the problem into sub-problems and we will apply the same technique for each and every sub-problem, and finally we will combine the solutions of this all the sub-problems together, gives the solution for the given problem. That is about the divide and conquer. And the next one is greedy method. In greedy method, the general technique is input set will be there. Some constraints will be applied on the input set. The input set which satisfies the constraints will be taken as a subset, and with this subset we will find the solutions with these subsets, which are all known as feasible solutions. Among all the feasible solutions, we will find an optimal solution based on a minimization or maximization problem. For example, if you take the problem knapsack problem, it comes under the minimization problem. Traveling salesperson problem comes under the minimization problem. Sorry, knapsack is a maximization problem, and job sequencing is a maximization problem. Traveling salesperson problem is a minimization problem. So, depending upon the minimization or maximization, optimal solution will be defined. And the next method is dynamic programming. So it is a general method for dynamic programming. In dynamic programming, solution will be obtained between the stages. For example, stage 1 input output is input to the stage 2, and stage 2 output is input to the stage 3. Finally, stage n minus 1 output is input to the stage n. In between the stages, the output will solution will be obtained for the problem. Next, coming to the backtracking. Backtracking is an algorithm design technique used to solve a problem with the help of an incremental method. It uses regression approach to solve the problems. For example, see the applications for backtracking. The first application for backtracking is a 4 queens problem. Generally, it is referred as a n queens problem. If n is 4, it is referred as a 4 queens problem. If n is 8, it is referred as a 8 queens problem. And one more application for backtracking is a sum of subsets problem. So see the problem here. The 4 queens problem is you have to place a 4 queens on 4 by 4 chessboard. That is the problem. Placing 4 queens on the 4 by 4 chessboard. And sum of subset problem is there will be given n positive integers or numbers. We have to find the subsets from this input set such that the sum of subsets of the elements or numbers should be equal to the that is the sum of subsets problem. So given n positive integers or numbers, and the problem is to find the subsets of the numbers whose sum should be equal to the and there are some more applications for backtracking. So this is first application, n queens problem, sum of subsets problem, knapsack problem, and Hamiltonian cycle problem, and graph coloring problem. Totally there are 5 applications for backtracking algorithm design technique. So again come here. So it is an backtracking. Backtracking is an algorithm design technique used to solve problem by an incremental approach. It uses recursive procedure to solve the problem. In backtracking, the solution vector, the solution will be expressed as a n tuple x1, x2, and so on xn, where x1 should be either 0 or 1. If you consider x1, it will be 0, sorry, it will be 1. If you didn't consider the x1, it will be considered as a 0. Okay. So here in the input set, we will apply two constraints. The two constraints that must be satisfied on the input set are implicit constraints and explicit constraints. These two are very important. Among input set, we have to apply these two constraints, implicit constraints and explicit constraints. For example, let us learn about what are implicit and explicit constraints. So coming to the implicit constraints, for example, see here, take the 4 queens problem. So what is the problem? The problem is to place 4 queens on the 4x4 chessboard. Here, the explicit constraint is total how many queens are there? 4 queens, and each row 1 queen should be placed. That is the explicit constraint. That means on each row there should be 1 queen. Okay, and implicit constraint is, the constraint is no 2 queens should attack with each other. That means no 2 queens should be on the same row or same column or in the diagonal. That is the implicit constraint. Okay, these are the two types of constraints that must be applied on the input data set. Okay, the difference between implicit and explicit constraints is, with the help of if you apply explicit constraints on the data set, you can get the solution as a 4 power 4 tuple solution. That means n is 4 here. So 4 power 4 solution spaces will be, solution vectors will be obtained. Okay. So if you apply implicit constraints also, then the solution space will be reduced from 4 power 4 to the 4 factorial 4 tuple solution. Here the tuple means it consists of 4 elements, 1, 2, 3 and 4. Here these represents the queens, queen 1, queen 2, queen 3 and queen 4. So these are the explicit and implicit constraints. Coming to the sum of subsets problem. Here the problem is to find the subsets whose sum should be equal to the m. Here what are the elements? 11, 13, 24, 7 are the elements and the m is 31. So here you are having two subsets. First one is 24 comma 7 is one subset because 24 plus 7 is equal to 31, and next subset is 11, 13 and 7. 11 plus 13 is 24, 24 plus 7 is the 31. Here the explicit constraints are xi belongs to j, j is an integer. You can take any integer from the set, any integer, either 1, 2, 3 or 4. And next implicit constraint is no two xi can be same and the sum of xi should be equal to the m. This is the implicit constraint. Okay, understood? Explicit constraint means you can take any element from the set, and implicit constraint is whatever the elements you are taking from the set, the sum of those elements should be equivalent to the m. That is the implicit constraint. Okay, so backtracking is nothing but modified process of brute force approach. Okay, here we will systematically find out the solution. Clear? If the solution is not obtained, then we will stop the searching the solution and we will find the solution from the next element. Okay, clear? That is about the backtracking. See here, general method of backtracking. So see the solution. So what is the 4 queens problem? 4 queens problem is to place 4 queens on 4x4 chessboard such that you have to satisfy the two constraints, implicit constraints and explicit constraints. So what is implicit constraint? Sorry, explicit constraint. On each row 1 queen should be placed. And what is implicit constraint? No 2 queens should attack with each other. That means no 2 queens should be on the same row, same column or in the diagonal. Okay, so start the solution here. First queen is placed in the first row, and can we place next queen in the second row first place? No, because it comes under same column, and second row second place comes under diagonal. We can place in the second row third column. And next, coming to the placing queen 3, we can't place queen 3 in the third row. Why? Because if you place queen 3 in the third row first column, it will comes under the same column. We cannot place in the third row second place because it will comes under same diagonal. In third row third place also we can't place, and in the fourth place also we can't place the queen 3. Okay, next we'll go to the fourth row. Fourth row, in the first place we can't place the queen 3, in the second place we can place the queen 3, but here queen 4 is not placed, so we will apply the backtracking. So here the backtracking comes into the picture. So what is the need of backtracking? We are finding the solution in the systematic way. At the time we came to know that there is no solution for this any queen, then we will apply the backtracking. So here where we apply backtracking, we have placed queen 2 here. By placing queen 2 in the second row, third column, solution is not obtained. So we'll apply backtracking. We place the queen in the next location. So we'll place the queen 2 in the second row, fourth location, and apply the same procedure. Here you can place the queen 3 in the third row, second column. Again, if you find the systematic procedure, queen 4 will not be placed. So again we have to apply the backtracking. So where the backtracking has to be applied, first you apply backtracking by moving queen 2 from one location to the another location. Next, if you apply backtracking and again you search the solution, there is no final solution. So again apply backtracking. So if you again apply backtracking, you move the queen 1 from position 1 to the position 2 in the first row. Here queen 1 is moved from first position to the second position. Again start the procedure. So queen 2 you can't place here, and here also you can't place, here also you can't place. In the fourth position you can place the queen 2, and next check the queen 3 you can place in the first position, and you can check the queen 4 you can place in the third position. Therefore, the solution vector for the 4 queen problem is 2, 4, 1, 3. So dear students, please make a note that each row itself represents the queen and the solution vector represents the columns. That means first queen is placed in the second column. Each row itself represents the queen. So first queen is placed in the second column, second queen is placed in the fourth column, third queen is placed in the first column, and fourth queen is placed in the third column. So this is the solution vector for the 4 queens problem, 2, 4, 1 and 3. So now see the backtracking general method here. T of x1, x2 and so on, xk minus 1 is the partial solution. So see here, for each x of k belongs to T, you will repeat the procedure. If backtracking, we will apply backtracking. If it is true, then the solution will be obtained. If it is not true, then all queens are not, we will check whether all queens are placed or not here. If k is less than n, k means it represents the queen. If example k equal to 1 means you are placing queen 1, k equal to 2 means you are placing queen 2, k equal to 3 means you are placing queen 3 and so on. If all queens are placed, then the algorithm will be terminated. If all queens are not placed, again backtracking will be applied. Backtrack of 1 represents placing queen 1, backtrack of 2 represents placing queen 2 and so on. First you will start the solution systematically and you will check whether the solution will be obtained or not. You apply backtracking. If the solution is obtained, then you will write the solution vector as a output. If solution is not obtained, again you will apply the backtracking for the all the things. So this is the general method for the backtracking. Clear all of you? Thank you.